What's the derivative of a product of two functions? The derivative of a product is given by this, the product rule. The derivative of f times g is the derivative of f times g plus f times the derivative of g. There's a bunch of things to be warned about here. This is the product of two functions, but the derivative involves the sum of two different products. It's the derivative of the first times the second plus the first times the derivative of the second. Let's see an example of this rule in action. For example, let's work out the derivative of this product, the product of 1 plus 2x and 1 plus x squared. All right, well, here we go. This is the derivative of a product, so by the product rule, I'm going to differentiate the first thing, multiply by the second, and add that to the first thing times the derivative of the second. So it's the derivative of the first term in the product times the second term in the product, derivative of first function times the second, plus the first function, 1 plus 2x, times the derivative of the second. Well, that's an instance of the product rule. Now this is the derivative of a sum, which is the sum of the derivatives. So it's the derivative of 1 plus the derivative of 2x times 1 plus x squared plus 1 plus 2x times the derivative of a sum, which is the sum of the derivatives. Now the derivative of 1, that's the derivative of a constant function, that's just 0. This is the derivative of a constant multiple, so I can pull that constant multiple out of the derivative. Times 1 plus x squared plus 1 plus 2x times the derivative of 1 is 0, it's the derivative of a constant, plus the derivative of x squared is 2x. All right, now I've got 0 plus 2 times the derivative of x. The derivative of x is just 1, so that's just 2 times 1 times 1 plus x squared plus 1 plus 2x times 0 plus 2x. So there it is. I could maybe write this a little bit more neatly. 2 times 1 plus x squared plus 1 plus 2x times 2x. This is the derivative of our original function, 1 plus 2x times 1 plus x squared. We didn't really need the product rule to compute that derivative. So instead of using the product rule on this, I'm going to first multiply this out and then do the differentiation. Watch. So this is the derivative, but now I'm going to multiply all this out, right? So 1 plus 2x cubed, which is what I get when I multiply 2x by x squared, plus x squared, which is 1 times x squared, plus 2x times 1. So now I could differentiate this without using the product rule, right? This is the derivative of a big sum, so it's the sum of the derivatives. The derivative of 1, the derivative of 2x cubed, the derivative of x squared, and the derivative of 2x. Now the derivative of 1, that's the derivative of a constant, that's just 0. The derivative of this constant multiple of x cubed, I can pull out the constant multiple. The derivative of x squared is 2x, and the derivative of 2 times x, so I can pull out the constant multiple. Now what's 2 times the derivative of x cubed? That's 2 times the derivative of x cubed is 3x squared plus 2x plus 2 times the derivative of x, which is 2 times 1. And then I could write this maybe a little bit more nicely. This is 6x squared plus 2x plus 2. So this is the derivative of our original function. Whoa! What just happened? I'm trying to differentiate 1 plus 2x times 1 plus x squared. When I just used the product rule, I got this, 2 times 1 plus x squared plus 1 plus 2x times 2x. When I expanded and then differentiated, I got this, 6x squared plus 2x plus 2. So are these two answers the same? Yeah, these two answers are the same. Let's see how. I can expand out this first answer. This is 2 times 1 plus 2x squared plus 1 times 2x plus 2x times 2x is 4x squared. Now look, 2x squared plus 4x squared gives me 6x squared, and 1 times 2x gives me this 2x here. These are in fact the same. Should we really be surprised by this? I mean, I did do these things in a different order. So in this first case, I differentiated using the product rule, and then I expanded what I got. In the second case, first I expanded, and after doing the expansion, then I differentiated. More succinctly, in the first case, I differentiated, then expanded. In the second case, I expanded, then I differentiated. Look, you'd think the order would matter. Usually the order does matter. If you take a shower and then get dressed, that's a totally different experience from getting dressed and then stepping into the shower. The order usually does matter. And you'd think that differentiating and then expanding would do something really different than expanding and then differentiating. You've got real choices when you do these derivative calculations, and yet somehow mathematics is conspiring so that we can all agree on the derivative, no matter what choices we might make on our way there. And I think we can also all agree that that's pretty cool.